The main takeaway is that VLM, i.e. 3D, bridges the gap between 2D vision and 3D spatial reasoning without requiring expensive 3D sensors. To understand how, let's look at the current state of vision language models, or VLMs. While VLMs excel at understanding 2D images, they struggle with tasks like 3D object detection or spatial reasoning. VLM, i.e. 3D, solves this by extracting both implicit and explicit 3D geometric representations directly from standard RGB video sequences. This allows the model to perceive depth, layouts, and precise coordinates using only a standard camera feed. The key problem is that current 3D-Aware VLMs rely on a single, coarse representation of the world. As shown in Figure 1, existing models build a 3D cognitive map, which captures global layouts but lacks local geometric details. Alternatively, robotic systems use explicit 3D reconstruction maps like point clouds, but these require specialized, expensive 3D sensors. VLM, i.e. 3D, addresses this limitation by combining both approaches, giving the language model access to both abstract global layouts and precise, quantitative local structures. The core breakthrough lies in VLM, i.e. 3D's three-stream processing pipeline. Looking at the framework overview in Figure 2, the model processes RGB frames through three parallel paths. First, a 2D visual encoder extracts standard visual tokens. Second, a 3D geometry encoder generates implicit geometry tokens, or IGTs, for high-level spatial priors. Third, a lightweight embedding module converts reconstructed 3D attributes, like depth maps, into explicit geometry tokens, or EGTs. These three streams are then fused to create a rich, 3D-aware representation. The main point here is that implicit and explicit tokens serve complementary purposes. Let's break down how they work. Implicit geometry tokens, or IGTs, act like a human's abstract mental map, capturing the overall layout of a room and the relationships between objects. On the other hand, explicit geometry tokens, or EGTs, act like a tape measure, providing precise, quantitative spatial measurements. By combining the abstract context of IGTs with the mathematical precision of EGTs, the model achieves a complete spatial understanding. The main takeaway is that the 3D-Aware adapter bridges the gap between abstract and concrete spatial data. As illustrated in Figure 3, the adapter uses an implicit-explicit attention, or IEA, module. This module performs multi-head cross-attention, using the compressed implicit tokens as queries and the explicit tokens as keys and values. This allows the model to dynamically align the global scene layout with local depth details. Finally, these fused 3D features are added directly to the 2D visual tokens, preserving original visual semantics. The main takeaway from the experiments is that VLM, i.e. 3D, outperforms existing RGB-only methods across multiple 3D benchmarks. As shown in Table 1 on the Scan 2 Cap Dense Captioning task, VLM, i.e. 3D, achieves a score of 80.4, significantly outperforming the baseline Quinn 2.5 VL. It also shows massive improvements in 3D visual grounding and 3D video detection. Remarkably, it achieves these competitive results without requiring any actual 3D sensor data, proving that 2D video contains sufficient geometric information when properly extracted. The main takeaway regarding limitations is that VLM, i.e. 3D, is highly efficient but still depends on the accuracy of its underlying geometry encoder. Because the explicit tokens are generated from reconstructed depth maps, any errors in the initial 3D reconstruction can propagate to the language model. Additionally, incorporating the 3D-Aware adapter introduces a minor latency trade-off, reducing the inference speed slightly from 7 frames per second to 6 frames per second on a single GPU. However, this remains highly practical for real-world deployment. The final takeaway is that VLM, i.e. 3D, represents a major step forward for accessible embodied AI. By enabling robust 3D spatial reasoning from standard RGB cameras, this framework eliminates the need for expensive LiDAR or depth sensors in many applications. Future work will focus on optimizing the inference speed and exploring more advanced 3D representations like Gaussian splats. This technology could soon allow household robots and autonomous systems to navigate and interact with their environments using simple, low-cost cameras.